Hey, welcome. Right now, all around you, there's a hidden world in constant motion. It's a world of transformation, where things change their very nature. We're talking about chemical reactions, and they are the invisible engines of our daily lives, from the food we eat to the air we breathe.
So, have you ever really thought about this? You leave a perfectly shiny iron nail outside, and, over time, it gets covered in this reddish-brown, flaky stuff. What is actually happening to it? Well, that simple mystery is a perfect example of a chemical reaction. And in this explainer, we're going to pull back the curtain and see exactly what's going on.
And it is not just about rust. Think about it. Milk souring on a hot day, the magic that happens when you cook food, your own body digesting a meal, or even just taking a breath. In every single one of these cases, the original stuff is changing its identity and becoming something totally new. And whenever that kind of chemical change happens, we can say a chemical reaction has taken place.
So, here's our plan for today. First, we'll learn how to spot a chemical reaction. Then, we'll get into the special language chemists use to talk about them. After that, we'll cover the one fundamental rule they all have to follow, explore a few common types, and finally bring it all back to our everyday world.
Okay, let's dive right in. How do we know for sure that a chemical reaction has happened and not just, say, a physical change like ice melting into water? Well, it turns out there are a few dead giveaways to look for.
So how do you spot one of these in the wild? Well, chemists look for 4 key clues. You might see a sudden, dramatic change in color, or maybe bubbles of gas start appearing out of nowhere. Sometimes you can mix 2 liquids and poof, a solid appears. That's a change in state. And finally, you might literally feel the reaction as the container gets surprisingly hot or cold, a definite change in temperature. If you see any of those, you can be pretty sure you've got a chemical reaction on your hands. Now, trying to describe all these changes with regular words can get really long and honestly kind of clumsy. So to speed things up, chemists came up with a special kind of shorthand, a really powerful symbolic language to represent reactions, and we call it the chemical equation.
Okay, take this sentence for example. It tells us everything we need to know, right? But just imagine having to write that out for every single reaction. It's super descriptive for sure, but it is not efficient at all. Chemistry really needed its own alphabet.
And this is what's so cool. You can see the evolution right here. We can shorten that long sentence into a word equation, which is a little better. But the real game changer is the chemical equation on the right. Using symbols, it instantly shows us the reactants, the things we start with, magnesium and oxygen, and the product we end up with, magnesium oxide. It's the universal shorthand of chemistry.
But just writing down the symbols isn't quite enough. See, every chemical equation has to follow one of the most fundamental laws of the entire universe. You can think of it like balancing a cosmic set of books, where nothing can ever be created out of thin air or just vanish.
And this is it, the law of conservation of mass. All it really means is that the total mass of the stuff you start with has to exactly equal the total mass of the stuff you end up with. In other words, the number of atoms of each element has to be the same on both sides of that arrow. Atoms aren't created or destroyed, they just get rearranged and find new partners.
Let's look at a real example, the reaction of iron with water. This right here is what we call a skeletal equation. It's like the basic blueprint. But look closely. On the left side, we have 1 iron atom, but on the right side, we have 3. Uh-oh, the scales are tipped. This equation is breaking the law. We gotta fix it.
So how do we fix it? Well, balancing an equation is basically like solving a puzzle. We can't change the compounds themselves, like we can't change H2O to H3O, but we can change how many of each molecule we have. As you can see from the steps here, the trick is to start with the most complicated molecule first. In this case, it's that iron oxide. We'd balance its 4 oxygen atoms first, which then throws the hydrogen out of whack, so we fix that next, and then the iron last. It's a step-by-step process of adjusting the numbers out front until every single element adds up perfectly.
And voila! Here is the final balanced result. Just look at that tally. 3 iron atoms on the left, 3 on the right. 8 hydrogen on the left, 8 on the right. 4 oxygen on the left, 4 on the right. It's perfect! The books are balanced, the law is satisfied. This is the correct, complete chemical equation for this reaction.
Okay, so now that we understand the language and the rules, we can start to see that reactions often follow common patterns. You can almost think of them like different types of stories. Let's take a look at 3 of the most common plots in the world of chemistry.
First, you've got your combination reactions. That's a story of coming together, where 2 or more things join up to make one new thing. The exact opposite is a decomposition reaction, where one complex thing breaks apart into simpler pieces. And then you have my favorite, displacement reactions. This is where one element basically cuts in on the dance floor and swaps places with another. Let's zoom in on one of those displacement reactions. Check this out. If you take a shiny iron nail and dip it into a bright blue solution of copper sulfate, something really dramatic happens. You wait about 20 minutes, and when you pull it out, the nail is coated in this brownish stuff, and the beautiful blue color of the solution has gotten way lighter.
So what in the world is going on at the atomic level? Well, it's that dance floor swap we were talking about. The iron, because it's more reactive, literally cuts in and kicks the copper out of its partnership with the sulfate. That brownish coating you see on the nail, that's pure copper, and the iron has now taken its place in the solution, which is why the blue color fades. It's a classic chemical swap meet.
All right, let's bring this all the way back home. Let's see how these ideas play out in the world we can actually see and touch, especially when it comes to one of the most common reactions out there, oxidation. Oxidation, which is just a reaction involving oxygen, has two really common effects you've definitely seen. The first is corrosion. You know that rust on the iron nail from the very beginning of our talk? That's corrosion, and it's a huge problem, causing damage to cars, bridges, you name it. The second big effect is rancidity. This is what happens when fats and oils in your food react with oxygen, they spoil, and their smell and taste get all funky.
And here is a fantastic, real-world example of putting chemistry to work. You ever open a bag of chips and wonder why it seems half full of just air? Well, that's not just regular air. It's usually pure nitrogen gas. Food manufacturers flush the bags with nitrogen to push out all the oxygen, which slows down that oxidation process way down and keeps your chips from going rancid and tasting stale. Pretty clever, right?
So, there you have it. We went from a simple rusty nail all the way to the gas in a bag of chips. We've seen that what looks like a simple, everyday change is actually a really cool story, written in the elegant language of chemical equations. So, the question I want to leave you with is this. Now that you know the basics of how to read this hidden language, what other chemical stories will you start to notice unfolding all around you?